All right. So what we're going to talk about today is kind of the, if you will, backbone of doing what we would typically refer to as analysis in mathematics, and that's the concept of a function. So we will deal with functions all semester. We'll talk about different types of functions and different properties those different types of functions have as we go along. But today we're just going to focus on the basic concept of what a function is, and then the idea of function notation and how you do evaluation of functions. Okay, so that's today's idea. All right, so not to add suspense here, is what we're talking about is a function. So a function is a rule. Okay? We start with a set A. The function is going to take something out of that set A. We refer to that set A as the domain of the function. Domain is the we like to think of functions as a machine. The domain is the input into the machine. It's what you stick into the machine. Okay? You put something in, you get exactly one thing out in another set. We refer to that other set as the codomain. So the stuff that you put in, called the domain. Okay? The inputs come from the domain. The codomain is just where your outputs live. Right? Or set that happens to be. All right. There's a specific set, a piece, a part of the codomain that we refer to as the range. The range of a function is the set of all possible outputs. So to give you an example of what I mean by this, maybe you have a function that takes a number and squares it. Takes the square of it. Okay? If I take the square of any number, doesn't matter if it's positive or negative or zero, what kind of a number do you get out if you square the number? Positive, right? It always has to be positive, right? Because if I multiply a number by itself, it's either a positive times a positive, which gives you positive, or it's a negative times a negative, which gives you a positive, right? Or if you take 0 times itself, you get 0. Okay? So you get 0 or something positive, right? So in that case, the range would be anything bigger than or equal to 0. Okay? That's what we mean by the set of possible outputs, right? You can get 0, you can get anything positive, but you can't get anything negative. Okay, so that's what we mean by the range. All right. So let's look at an example here. An easy way to represent a function when it's a small number of inputs and outputs is through the use of ordered pairs. Okay? One of the things that we're going to do with functions later on is graph them. When you do things graphically, you think of having an x and a y, ordered pair ideas. It's exactly what we have here. So your first coordinate in your ordered pair would represent the input. The second coordinate represents the output. Okay? So for this particular function, when you plug in 1, you get out 3. When you plug in 2, you get out -1. When you plug in 4, you get out 3. That's what that says. Okay? So let's see if we can identify what our domain and our range are. So we said the domain is a set of all the inputs. What are your inputs here? 1, 2, and 4. So if we just write it as a set, just write it as 1, 2, 4. What's our range? Okay, so we've got outputs of 3, -1, and 3, right? I don't need to write the 3 twice because it's the same number. And usually, don't have to, but usually we'll write things smaller to bigger. So I'll write it as -1 and 3. So again, the domain, the stuff that goes in, the range is the stuff that comes out. Does that make sense? All right. Now, remember also it says a function has to, if I put one thing in, I'm only allowed to get one thing out. Okay? So let's look at this next example. Is this even a function? No. Look at this second. Look at these two here together. The first one would say I plug in 3, I get out 1. This one says I plug in 3, I get out 4. I have two outputs assigned to the same input. So this is not a function. Okay? This is not a function. The input 3 is assigned two outputs, 1 and 4. So not a function. Does that make sense? And again, if you have an input, you can only have one output. So if you've got it listed like this, you better only see each input listed exactly one time. If you see an input listed twice, it's not going to be a function. Unless somebody wrote the same ordered pair twice. Which they're not going to do. Okay? All right, so again, if you've got a small set, writing things as sets of ordered pairs might work. You might also see these arrow diagrams and determine whether or not you've got a function. So looking at this first example with my arrow diagrams, notice here my A is representing my input set, my domain. My B is representing my codomain, okay? Where the inputs live, where the outputs live. And then the arrow is just doing your assignment, right? I plug in 1, I get out 3. I plug in 2, I get out 5, and so on. So does that first one represent a function?
Yes.
Yes, good. How about the second one?
Yes.
Also yes, right? Each one only goes to one thing, right? What about the last one? No. Okay. Notice in the last one we got a couple of problems, right? Tell me an input that's mapped to two outputs. 1, right? 1 goes to 3 and 5. Can you tell me another one? 3 goes to 8 and 11, right? Does that make sense? Okay. If I look at the first, since the first two are functions, can you tell me what the domain of each of them is? Good, yeah, 1, 2, 3, 4, 5. By the way, if you specify domain, that means everything in there can be plugged in, right? When you say domain of a function, that means every single thing in that set is allowed to be plugged in. There's not anything that you can't plug in. We will be looking later on today for domains of functions that are written in what we refer to as function notation, which we'll do here in a second. We'll be looking for what are allowable inputs. What are we allowed to plug in? We'll identify the domain that way. Okay. All right. For the first one, I forgot to close off my brace for the domain. For the first one, what's the range?
3, 5, 8,
Good. 3, 5, 8, 11, 12. What about the second one?
3, 5, 8.
3, 5, and 8. Good. Because those are the ones that are the only outputs, right? So notice here, this is what we mean by the difference between codomain and range. Codomain just says these are where the outputs can land. The range is literally what are the outputs. Okay? So here the outputs actually ended up being the entire codomain. Over here, the range was just a piece of the codomain. Is that okay? All right, so let's see if we can move on to more, I'll say, interesting functions. Okay? All right, so function notation. This is a way to express kind of a rule where we have lots and lots and lots and lots of things that we can plug in for the input, right? It wouldn't be very useful here to try to list this out as a set of ordered pairs. Because notice I can plug anything I want in for x, right? Including fractions and square roots and anything else you wanted to do, right? I can plug in anything I want. I'm not going to have any issues. So I wouldn't want to try to list it out as a set of ordered pairs because it's literally impossible to list it out as a set of ordered pairs. Okay? So this function notation just gives us a rule of, it tells you, if I plug in something for x, what am I supposed to do with it? So in this case, when I plug in something for x, I'm going to multiply it by the 5 and then subtract the 2. Okay? Think of this x as a whole. And whatever goes inside those parentheses is what you're going to fill the hole with. Okay, that's what the function notation means. So literally whatever's inside these parentheses here is what you're going to take out the x and replace it with. Okay? So over here, when we read it as f of x, in this case we would say f of 4. I'm going to take out the x and replace it with a 4. So you take the input, multiply it by 5, subtract the 2. Simplify it, we get 18. Do the same thing with the negative 2. Be 5 times the negative 2 minus 2. That gives us negative 12. Is that okay? Okay. Now again, it's literally whatever is inside those parentheses goes in for the x. It doesn't matter what's inside the parentheses. That literally goes into where the x is, right? So this one has f of a cubed. You're going to replace the x with a cubed. Okay? Doesn't matter what we're plugging in there. Could be a number, could be a letter, could be an emoji. Doesn't matter what it is. You're going to do that to that thing that you plugged in. Okay? Not a lot of simplifying that you can do because I don't know what a is. So I can write it as 5a cubed minus 12. That's as good as it gets. Okay? That literally is the output. What would you do for the next one? Yes. Oh, it's just a 2. Sorry. Yep. Yep. Sorry. I was still thinking about the previous problem where there was it was a minus 12, and I just wrote the same exact thing. Sorry. It's a 2. Yep. Thank you for asking. All right. What about the next one? What would you do? Good. So again, the first thing what we would do is we take out the x and put in a minus 5 for the x. Okay? Since that x is a single thing, I want to make sure I put the a minus 5 in parentheses. So that now we want to make sure we distribute the 5 through, right? So you would have 5a minus 25 and then minus a 2. So you get 5a minus 27 when we simplify it. Does that make sense? Again, the hardest thing to get used to, at least for students in my experience, is making sure that you take out the x and put in absolutely what you see inside the parentheses for the x. Okay? Don't try to do anything fancy with it. Literally remove the x, put the other thing in. Okay? Does that make sense? All right. Work on the next one for a minute. Just the g of t. Just work on that one for a minute. And then we'll talk about it. We'll come back and talk about it together. Ready to chat about it? Yeah. What did you get for the first one? What did you do?
0 to 2 minus 5 over 0 plus 1.
Good. Yep. Take out the t, put in the 0, and when you simplify, you get -5. Is that what everybody got for that one? Yep. Second one. Okay. Yep. You got 9 minus 5 over 3 plus 1 gives you.
Yeah, 4 over 4.
Yeah, you got 4 over 4, right? Should we get 1? Yeah. Yep. All right. What about the next one? What is it? What's your first step look like for the next one?
A plus 2.
Okay.
Squared.
Yep.
Over A plus 2 plus 1.
Good. Yep, I agree. Again, literally take out the t, take out the variable, and put in what's inside the parentheses, right? In this case, it's a plus 2 is inside the parentheses, even though my a kind of looks like a 9, doesn't it? Sorry about that. Okay. So far, so good? Okay. The denominator should be pretty easy to simplify. What do you get in the denominator? A plus 3? Good. On top, if I want to simplify it, I would need to multiply out the a plus 2 squared, right? Let me just do that off to the side. If I want to do a plus 2 squared, remember that's a plus 2 times a plus 2, right? So what do you get when you multiply that out? Good. A squared plus 4a plus 4. Don't forget to FOIL, right? Make sure that when you multiply this out, everything in your first piece gets multiplied by everything in the second piece, right? A times A times 2, 2 times A, 2 times 2, right? Don't just try to distribute the squared over the plus. Okay? That'll get you lots of red ink on your paper. Okay? All right. So going back over here again, you would get a squared plus 4a, and then plus 4 minus 5 gives you a minus 1 on the end. And that's about as good as you can do. Does that make sense? Okay. All right. The next one, the first two should be pretty straightforward, just plugging in the numbers, right? Just like we did before, you'd have square root of 7 minus 3 times 1. This gives you square root of 4, which is 2, right? And the next one is 7 minus 3 times negative 3. You'll get 7 plus 9, because you got minus a minus 9. So you get square root of 16, which is 4. Those two okay? Okay. The reason really why I put this one on here is for the last two parts. There's a difference between these two things, right? This says what?
Z squared.
Yeah, put z squared into the z, right? Take out the z, replace it with z squared, right? What does this one say to do?
Square root.
Yeah, take the square root of you take the square of the whole thing, right? There's a difference between the two, and that's one of the reasons why I put that on here. There's literally a difference between those two things. This one is square root of 7 minus 3z squared. Not a lot you can do with that. Square roots do not break up over sums and differences. That's literally all you can do. Okay? This other one says I do the square root of 7 minus 3z and then square the whole thing, right? That's different. And when we square the square root, what do we end up with? Just the 7 minus 3z, right? Okay. Those two things are not the same. Okay? This one says take out the z, replace it with z squared. This one says take the function, the whole function, and square it. Different things. That was the reason why I wanted to do that one. Any questions on the function notation at all? Okay. All right. So sometimes when you do functions, you have to define them in pieces. To give a really straightforward example of this, if you look at taxes, doing income taxes at all, it's a big old piecewise defined function. Okay? The more money you make, the higher your tax percentage goes. So the tax percentage depends on how much money you make, and so you've got it in pieces. Okay? So piecewise functions really do pop up in practice. When we have the piecewise defined functions, pardon me, you look at what the conditions are to figure out which piece you plug things into. Remember, functions, how many things are you allowed to get out if you plug one thing in? One, right? So you never ever, in a piecewise function, plug in the number in multiple places. You only plug it in one place, okay? So the conditions tell you where to plug it in, okay? You're only going to plug a number into the first one if that number is less than or equal to 1. You only plug it into the second one if it's bigger than 1, okay? So looking at the first example, if I look at f of negative 1, which piece are you going to plug the negative 1 into? The top piece, right? You're going to plug it into the 4 times negative 1 plus 1. Because negative 1 is less than or equal to 1. Where do you plug in the 4? The bottom one, right? Now, I put this one in here on purpose as well. Does this square apply to that negative sign? No. Okay? Remember your order of operations? If you think of a negative sign as negative 1 times something, you do exponents before multiplication. This says square it and then take the opposite. You don't square that negative. Okay? So that's why when I have negative 4 squared, I get negative 16. Not positive 16, because the square doesn't affect the negative. This is important to remember in your calculators, by the way. Okay? If you want to make sure you square that negative, you need to put it in parentheses before you do the squaring. Okay? Your calculator, if you type in, it will give you negative 16, like it's supposed to. Okay? If it was supposed to be this, then you'll get 16. So be careful with your parentheses. Okay? All right, what about the last one? Where do you plug 1 in? To the first one or the second one? Because of that equal sign right here, right? So you plug it into the top one. Oops. And get 5. Does that make sense? Okay. You tell me the next one. Where do you plug in the negative 3? The first one? Good. What do you get when you plug in negative 3? 1. Yeah, you get 1, right? Because you'll get square root of 1, which will give you 1. 5 times negative 3 will give you negative 15 plus the 16 gives you the 1 under the radical. Where does the 0 go? The bottom one. And what do you get when you plug 0 into the bottom one? 7. Good. Everybody okay with those two? And understand why we're plugging them into the different pieces? That's the important part with this, right? Making sure you understand where we plug them in. Okay. Where does the negative 2 go? In the bottom one, because again, that right there, right? It says if x is greater than or equal to negative 2. So it goes in the bottom. And what do we get? 23 when we're done. Because we'll cube the negative 2, gives us negative 8 times negative 2 is positive 16 plus the 7. That one okay? All right. Work on the next one. There's 5 of them to do there. Work on the next one, and then we'll chat about it. Yes.
I got kind of lost on the G.
Yeah.
So you cube this and you get negative.
Yep.
And then.
But you lost your 2. It's 2 times x cubed.
There it is.
There it is. Yep.
Thank you.
You're welcome.
So negative 2 is going into that. Oh wait. No, it plugs into the first one. Yeah.
Oops, sorry. Leaning on that and slipped. All right, let's go ahead and chat about it since there's chatter going on. So let's go ahead and chat. All right. What did you get for the first part? Negative 1/4? Good, because you'll put it into the top one in that case. And simplify, you'll get negative 1/4. What'd you get for the second one? 1/5? Because which piece does it go into? The middle one, right? And what'd you get for the third one? 2, because it goes into the last one. Okay. Everybody okay with those 3? And understanding why we plug it into those 3 pieces? Like I said, that's the big part. What about the next ones? Which one does the negative 1 go into? The top one, right? Again, we've got the equal sign up here. So the negative 1 is going to go into that top one. And so you get what?
Negative 1/3.
Negative 1/3. And which piece does the 2 go into? The second one, and you get 1/4. So what everybody got? Any questions on those at all? Okay. All right. So let's spend a little bit of time here, what we have left here, talking about domain and range when we've got our functions written in function notation. All right. So most of the time you'll be asked about domain. Range is a little bit more challenging. So a lot of times we'll look, if we want to look at range, we'll look at a graph. But in these 2 examples that I have here, we'll be able to get the domain and the range, or these 3 examples, I should say. We should be able to figure out what the range is too, just based on what we know about the different types of functions. All right, first off, when we're looking at domain, we want to think about looking at the example, or looking at the problem, looking at the function. What would cause a problem if we plugged something in? So what I mean, the 2 problems that we'll have right now that we'll be interested in is, am I dividing by 0 possibly? That's a bad thing, right? Another bad thing could be take the square root of a negative. Okay? Do I have either of those 2 things in this first one? No. So any number that I have, I'm allowed to square it. So in that case, our domain would be what we refer to as all real numbers. But we'll be writing these things at what we call interval notation. When I want to describe all real numbers in interval notation, I think about it, if I think about it graphically in terms of a number line, I can go as far as I want to the left and as far as I want to the right, right? If I shade all that in. So your left-hand side would go off to negative infinity. Your right-hand side would go off to positive infinity. So your domain, your interval notation is just using endpoints to describe that. Okay? We never, the parenthesis means that the endpoint would not be included, and we'll use a bracket for included. Okay? In this case, infinity is not a real number, so we would always use a parenthesis on the infinity. Okay? How about the range, though? Remember your range is outputs. Yep, good. So think about what your outputs can be. What's the smallest output that you could ever get just for the x squared? What's the smallest thing that you can get out? 0, right? And then what are you doing with the output? After you square it, you add 2. So what's the smallest possible thing that you could ever get out of this function? 2. Is there a biggest possible thing that you can get? Infinity, right? You go off to infinity, correct? So if you think about it just as an inequality, your range would be anything greater than or equal to 2. In interval notation, we would write it this way. And let me show you what that looks like from a number line perspective. On a number line, you would put a closed dot, right? And then shade it off to the right. That would represent everything bigger than or equal to 2. We agree with that? Okay. So notice for our interval, another way to think about it would be we could go all the way this way, right? And we use that kind of bracket to denote the closed dot. So again, the bracket is included. Parenthesis means it's not included. Okay. Let's look at the next one for domain and range. Now, I just told you, for right now, domain purposes, there's 2 big issues you have to worry about. Could I possibly divide by 0? Could I possibly take the square root of a negative number? We could possibly do a square root of a negative here, right? So when we do want to do our domain, we need to make sure that our x minus 3 is not negative, right? It could be greater than or equal to 0. It's okay to take the square root of 0, but I can't take the square root of anything negative. So if x minus 3 needs to be greater than or equal to 0, our x needs to be greater than or equal to 3. I want to write this in interval notation. Again, sometimes I like to think of it as a number line first. Would I use an open or a closed dot at 3? It'd be closed because it's equal, right? We would fill it in. And then since it's greater than, will we shade to the right or shade to the left? Right. To the right? And of course I erased it when I did that. So we would do the right, right? Because it's bigger. Okay, so how would I write that interval notation then?
A bracket 3.
And then comma, infinity. What will we put on the end? Parenthesis, good. Always is a parenthesis on the infinity, right? Okay. That was weird. What are you doing? Computer is possessed today. All right, let's think about the range now. Remember this, when we write square root, we mean principal square root or positive square root, non-negative square root. So what's the smallest the square root could ever be? 0. Is that the smallest it could ever do? What are we doing then? Adding a -1 to it or subtracting a 1. So the smallest answer you could ever get is -1. So what would your range be in interval notation? And then it could get as big as it ever wants, right? So it'd be -1, comma, infinity. All right. We'll practice more with interval notation next time. We'll finish off this handout, so make sure you bring it with you next time. And we'll also get a new one, 2.2. Watch your email today for instructions for WebAssign, making sure that you can all get in there. Again, your first WebAssign assignment for getting started is due tomorrow night. Okay? All right. Have a good one. We'll see you on Friday.